Hello, everyone. This is Fang. I'm from Zhejiang University. I'm glad to present our work, MDTP, a multi-source deep traffic prediction framework over spatial-temporal trajectory data. First, I will introduce the motivation of traffic prediction. Traffic prediction aims to predict the traffic conditions in the future, like traffic volumes, which serves many real-life applications, such as route navigation and back allocation. For better understanding, we give an illustration of traffic volume prediction. As you can see, there are four disjointed nodes where this node denotes a region in the map, while the directed edges represent the traffic flows among them. For example, the in volume of region R1 during T1 is true, and the out volume is 4, since there are one back and one taxi flowing in R1 and there are 3 backs and one taxi flowing out R1 during time interval T1. Finally, we get the traffic volume of all regions during T1, T2 until Tn, where Tn denotes the current time. Based on that, we can predict the traffic volume for the next time interval, T1 plus 1. Many studies have been proposed for traffic prediction. However, there are still 3 unsolved challenges. The first challenge is the multi-source data influence. Since different types of moving objects may have corrections when they move in similar traffic conditions. To verify such assumptions, we give visualization insights into the NYC data set. As expected, the taxis and bags have corrections in both spatial and temporal aspects. To overcome this challenge, we studied the multi-source traffic data-based traffic prediction. The second challenge is the dramatic spatial dependencies. Most of the existing methods are efficient since they assign edges in GCN models with static attributes with route distance and traffic context. To solve this challenge, we donate the edges of GCN models with dynamic traffic flows. The third challenge is the applicable uses. This is because network P puts attention on the demonstration of traffic prediction analysis, making it hard for users to apply it to real-world scenarios. To track this challenge, we developed a user-friendly interactive system, which supports 3 popular functions. Next, I introduce the related work. Existing traffic prediction methods can be broadly divided into traditional methods and deep learning methods. The traditional methods can be further classified into time series methods and machine learning methods. However, they mostly rely on the handcraft feature modeling and shallow models, showing limited performance. The deep learning methods include CNN-based, RNN-based, CNN-RNN-based, and the state-of-the-art GCN-based. Although they could achieve promising performance compared with traditional methods, they ignore the 3 challenges as we have detailed before. Next, I introduce the preliminaries. We first partition the city space into an I times J grid map, where each grid Ri denotes a region. Here, we call it as a node. Given a trajectory data set, we can calculate the in and out volume of each node based on 2 equations. Finally, to capture the dramatic traffic flows between nodes, we use the in and out volume as the directed edges in the graph modeling. Based on the nodes and edges, we build the traffic graph GT. Further, we can calculate the feature matrix XT and adjacency matrix AT. where xt denotes the in-out volume of each region and at denotes the volume flow between regions. Finally, we give the formal definition. Given a site G of a historical traffic graph and its feature matrix site and adjacency matrix site, we aim to forecast the future status xt plus 1 at the next time interval t plus 1. In the following, we present our proposed methods. Our framework contains two parts. In the first spatio-temporal feature modeling, multi-source traffic data is modeled in spatial and temporal aspects. In the second multi-source bridging, the spatio-temporal features learned from backs and taxis are merged together to capture the corrections between them. In the next, we detail these two parts. Specifically, given a traffic graph GT, we compute its input feature matrix and adjacency matrix. The graph convolutional layer is defined as follows. Then, we get the sequence of learned traffic states in the past as time intervals, which will be further fed into the LSTM model. It is worth mentioning that each traffic source will be considered in these phases. In the second stage, we propose two bridging methods, sum and concat. Concat is based on matrix multiplication operation, which is more suitable for traffic flows without big differences. In contrast, sum is based on matrix add operation, which is more general for different situations. Finally, we present the loss function, which considers in and out volumes of each node for different types of moving objects. Here, we analyze the experimental results. We use two real multi-source data sets, each of which includes both taxi data and back data. We compare MDTP with classical time series methods, traditional machine learning methods, and state-of-the-art deep learning methods. In addition, we adopt three popular evaluation metrics. We first study the prediction performance here. We only show the results of NYC data sets due to limited space. As observed, our methods outperform all baselines. This is because MDTP considers the corrections between backs and taxis, and it can learn more spatial-temporal features of the complex traffic network to further improve the prediction performance. Then, we study the multi-source effect. As expected, the sum and concat methods perform much better than single-source-based methods. We proceed to study the model efficiency and model scalability. The experimental results demonstrate the good performance of our methods. Besides, we also give deep insights into the temporal range effect. Specifically, we divide the NYC data set into three sub-data sets and verify the prediction performance of MDTP using the sub-data sets. As observed, MDTP shows stable performance under different temporal ranges. More experimental evaluations are omitted due to time constraints. At last, I conclude our work. The contributions of our work are as follows. First, we propose a traffic prediction framework over multi-source traffic data using spatial-temporal corrections between different types of moving objects. We present an effective thematic traffic network modeling approach to capture both spatial and temporal dependencies. We developed a new cross-platform system called MDTP+, which is useful to help apply our framework in real life. Experiments demonstrate the efficiency, effectiveness, and scalability of MDTP. Thank you for listening.